Hello everyone, this is Dr. Singha. After rocks form underground, they go through new set of changes. They get bent, they get broken, and it is called rock deformation. Let's talk a little bit about it. Here are some rocks that are horizontal. These are considered undeformed. According to the principle of horizontality, rocks form as horizontal layers. So when you find them as horizontal layers, that indicates nothing has happened in this case except uplift. But not all rocks stay like that. Here are some rocks that is found in San Pedro. You can see the bedding is actually curved. So this is not, these beds are not horizontal, they are bent. In other words, they are folded, and we call these rocks deformed rocks. Here is another example from San Pedro, White Point. These are sedimentary rocks, mainly shales. These rocks are supposed to be horizontal, and they are not horizontal, they are almost vertical in this area. So if you look at this rock here, this layer here, it is vertical, and all this rock is slightly inclined, and if you follow the rock, they are supposed to be nice and smooth and uniform and horizontal, but look, they are bending. You can see these rocks are bending. You can see these rocks when you go to the White Point and look at the corner. So these are bent rocks. We call them deformed rocks. Here are some rocks from Palmdale on Freeway 14 going north. So that's north. This side is north. And you can see these rocks. They are not horizontal. They are bent. Quite a lot of bending. So these are deformed rocks. In fact, this is the plate boundary between North American and Pacific plates. This is where this plate boundary is called San Andreas Fault. We'll talk about this a little bit later, but if you drive 14 north after in the Palmdale area, you'll see this road cut that's showing all the deformed rocks. Here's another very interesting area. This is a satellite image of the western Himalayan mountains. So on the north east side of the image, this area is the Himalayan. You can see there are snow-covered mountains. This is Pakistan, that is India, this is Afghanistan, and these are all countries marked by these white lines. But I would like you to notice the lines that going like this. These are actually rock layers. There's something really interesting here. In a different note, this here is a boundary of the Indian plate. Which collided with the Eurasian plate, which is here. So that's the boundary of the Eurasian plate. So what's in here? This is all the marine sediments that was in the Tethys Sea. So the Indian plate collided with the Eurasian plate because they were converging, and everything in between got squeezed into a whole group of folds that actually got pushed up to make these tall mountains that made the Himalayan mountain range. This is rock deformation seen from space. Here is an image of Southern California seen from space, and right here is Los Angeles Harbor College. And of course this is the Palos Verdes Peninsula and San Pedro right there, this area here, and this is the Central Valley. These are Sierra Nevada mountains. So all these wrinkles that you see on the surface actually is a result of deformation, rock deformation. So you can see in this area right here is all flat. And these are all sediments. And all these lines in here, you can see this is the Santa Monica Mountains right here. And these are San Gabriel Mountains. And San Bernardino Mountains and all this. So all these lines looking, this is Nevada. So all these lines are actually mountains formed by rock deformation, being pushed and pulled and broken and sliding apart. That's what's going on during deformation. We can define rock deformation as change in shape and or size. If you take a circle and say that's the original shape of a rock, and if you deform it to a situation like this, what changed was the shape. The size didn't change, the area didn't change. Take the same rock and make it look like this. What happened? The shape didn't change, but the size changed. So that's what happens. So if you have anything that is circular in the rock, they will end up as elliptical or a smaller circle. Generally, it never becomes large, it always gets smaller during deformation. So this is the definition of rock deformation. Rock deformation is caused by stresses. Stress is defined as a force with a direction. For example, if you have a rock that is 10 kilograms in weight, and if you let it go, it will go towards the center of the earth, which we call down. Now you can say 10 kilogram is the force and down is the direction. So 10 kilogram rock has a stress of 10 kilograms pointing towards the center of the earth. There are different types of stresses that acts as different locations on the earth with different types of movements. So the first stress type is called tension, and the movement is being pulled apart. I'm sure you remember that this movement occurs along divergent plate boundaries. So just to remind ourselves, we write divergent plate boundaries. So somebody asks you what kind of stresses are present along divergent plate boundaries, you say tension. And the opposite is true. Compression takes place when the stresses are directed towards a single point, and such things happen, or this kind of stresses occur along convergent plate boundaries. The third type of stress is called shear stress. Here the stresses are parallel to each other and they are not in the same line, they are just sliding past each other. Speaking of sliding past, of course you remember such things happen along transform plate boundaries. And then we have the fourth type of stress, we call that the hydrostatic stress. Hydro means water, static means non-moving, stationary. So if you have a body of water and if you think about a point underwater, inside the water, that point is being stressed or compressed from all directions. The point is right here and it is stressed from all directions. That happens deep underground. It is not a plate boundary. This happens underground. And we also have different types of deformation. The first type of deformation is called brittle deformation, and in this type of deformation rocks break. It happens when the rocks are stressed really fast. We are talking about few hundred years. And if the rocks are cold, which is the case near the surface of the earth, the rocks break. The second type of deformation is called ductile deformation. Rocks bend. They don't break, but they bend. When that happens during low deformation rates, when the rocks are stressed very slowly over periods of millions of years, then they slowly bend. And they also bend when they are warm, which happens when the rocks are deep inside the earth.
The determining factor as to whether or not you'll have what's called brittle deformation as opposed to ductile deformation has to do with the temperature that this is happening at. Here I have a piece of silly putty. If you haven't used silly putty before, it's very similar to chewed gum, except for it's not as gross to be handling silly putty as it is handling a piece of chewed gum, in that when it's really, really warm, it'll stretch easily, or when it's colder, or when the action upon it is very quick, whoop, there we go, it'll break rather than stretch. So that's the difference between ductile or malleable versus brittle deformation. Brittle deformation happens near the surface where it's colder, and you're going to have breaking and faulting of materials. Ductile transformation happens deeper in the surface where it's warmer.
After the rocks are deformed, they exist as broken and bent rocks at different angles. These angles are called the orientations of the rocks. So deformation is studied by measuring the orientation of the rock surfaces. There are two types of orientations: strike and dip. Let's talk about the strike first. Strike is defined as the direction from north of a horizontal line drawn on the rock surface. Let's try to understand the concept of strike by looking at an illustration that shows the rock surfaces and the strike. So here is a series of sedimentary beds. They are deformed, they are not horizontal, so they are bent. You are looking at only a small part of the bend, but here is the rock surface. And here is a body of water. And remember, the surface of the water is always horizontal. And this is north, so this arrow also is pointing towards north. You can draw all kinds of lines on this rock surface, like that, like this, like this, like that, like this, all kinds of lines, but not all of them is pointing towards north. So we have to find the direction of the line that is pointing towards north. So if you draw a line like this on the rock surface, then it is pointing towards north. So what is this angle relative to the north? And that is called the strike. So this line is called the line of strike. If the rock surface direction is like that, and if this is the north, the angle between the north and the rock surface is called the strike. Generally, the strike is recorded on maps that are horizontal surface representations. So to show the direction of the rock, you just draw a line to represent the strike. Here's another illustration that shows the concept of strike. Again, you have a body of water and that is horizontal. So when a rock is immersed in the water, the line that water makes on the rock, that means this line right here, this line here is a horizontal line. So if you can find the direction of that line, then that's the strike. So that's why we consider this line as a strike. Now, if you put water on this rock surface, drop some water, where would the water go? The water will drip down, slide down, flow down. That is the dip direction. That is marked by a short line perpendicular to the strike, and this is the horizontal, remember, and the angle from the horizontal, which is this one, is called the dip. Here are some rocks that you will find when you drive on 138 from Palmdale to Wrightwood area. These rocks are not horizontal, they are deformed. One side is being pushed up, so you can see that this side is pushed up. That's why it is not horizontal. Now if you imagine this underwater, then it will be like that, and that is the strike of these rocks. We go back to our earlier diagram. Now you can see the water body is horizontal and the rock surface, as this surface, this is the rock layer and this is the rock surface. Okay, so this is the strike, we talked about it. Again, if you drop some water on this surface, the water will hit the surface and then will go down, and that is the dip direction. Here is the horizontal and here is the rock surface, the horizontal and the rock surface. So the angle, in this case 30 degrees, is the dip. We can define the dip as the angle between the rock surface and the horizontal. The strike is the direction of the horizontal line drawn on the rock surface, and the dip is the angle between the rock surface and the horizontal. So if this is a rock surface and here is, say, water, a horizontal line, the angle between the horizontal line and the rock surface is called the dip, and the dip is marked by a short line drawn on on a strike line. So this is the strike, and dip is always perpendicular to the strike, so that indicates the dip. Generally this angle, let's say example, this is 47 degrees, and that number goes here, and in the map normally we assume that that is the north direction, and that is the strike. We'll talk more about this and do some experiments with this when you take the geology lab. When you do some hands-on activities on this, you will understand a little bit more what this is.
A complete planar orientation measurement consists of 3 parts: strike, dip angle, and dip direction. With planar measurements, the horizontal reference plane is really important. Strike is the directional bearing of the intersection line between the plane being measured and the horizontal reference plane. Because it is a line, the bearing of strike can have 2 possible directions that are 180 degrees from each other. Both are correct. The full description of strike is the directional bearing in either azimuth or quadrant format. Dip angle is the vertical angle between the plane being measured and the horizontal reference plane. A horizontal plane has 0 degrees dip, and a vertical plane has a 90-degree dip. Strike and dip angle are not enough, though. Those 2 alone result in 2 possible planar orientations that both have the same strike and dip angle. You should always take note of dip direction to clarify which plane you are describing. Dip direction is the direction in which water would flow down your measurement plane, and it is always perpendicular to strike. A simple cardinal direction for dip direction is usually sufficient. So, the complete description of a plane consists of strike, a directional bearing, dip, a vertical angle, and dip direction, a cardinal direction. The axis is the only transit that can simultaneously measure strike, dip angle, and dip direction on any plane at any angle. For all planar measurements, the lid of the axis should parallel the plane being measured, and the compass face should represent the horizontal reference plane, so it should be level. The major axis is your main measurement axis for strike and dip. If you can walk right up to the planar feature you're measuring, then you can use the contact method, which means putting the transit into direct contact with the outcrop. If you're lucky enough to have a nice flat surface that represents your measurement plane, the first step is to place the lid of the axis against that measurement surface. Make sure that the hinge is only rotating around its major axis. For strike and dip measurements, the minor axis should be locked in its 0-degree position. So when the compass face is level, press and release the needle button 3 times to allow the magnetic needle to reset. Then strike can be read off of either end of the magnetic needle, since strike has 2 possible correct directions. Dip angle can be read on either hinge dial, but make sure that you pay attention to the lid configuration. In standard configuration like this, dip angle should be read where the hinge dial meets the top of the dip indicator. In the alternate lid configuration, read the bottom of the dip indicator.
So here we again see undeformed horizontal beds in Grand Canyon area and dipping beds in Palmdale. If you look at this, this is the horizontal line and this is the dip angle, and that is the dip direction. The strike is going into the ground in this area. This location is called Vasquez Rocks. I think it's S. Vasquez Rocks. On 14, you can see that these rocks are dipping that way. So if that's the horizontal, and that's the dip angle, and that's the dip direction. Here is the Vasquez Rock again with the geology lab students visiting this area. You can see in here the rocks are dipping to your left like this, and that is the horizontal and that's the dip. These rocks actually don't stop here, they continue like that and actually come back towards the Earth's surface again 20 miles away to the east. Just look at, now you're looking at dipping sandstones or dipping rocks. Deformation causes different types of features called structures. There are 4 structures that we'll be talking about: folds, faults, joints, and lineations. So let's talk about folds first. Folds are bends in rock layers. They are caused by compression. If you take a piece of paper and push the paper from the edges towards the center, you'll crumple the paper, and those are actually folds. The same thing happens in rocks. There are 3 types of folds: anticlines, whose curvature is pointing towards the top, and then syncline, curvature pointing towards bottom, and then monocline, which has one curvature or one inclination. So if you look at this carefully, the anticline looks like the letter A, so that's very easy to remember, anticline. And then the other one is called syncline, or if you want, that's a Y syncline, but that I think doesn't help a whole lot. But if you can tell which one is the anticline, then the other one is the syncline. Cline refers to inclination, and inclination actually technically refers to the dip. So the anticlines dip outwards from the center. Synclines dip inwards towards the center. And monoclines has only one dip, only one side dips, and the other side is horizontal. That's how you identify these three different types of folds.
Compressional forces cause a buckling up of the land. While we have some layers buckling in an upward fashion and others in a downward fashion, both the ups and downs result from compression. You can't create a downward dip by pulling on a layer. You have to push it together. So here I have an up dip and a down dip just from compression. Here we have an example of a cross section of some strata that's been compressed. So we have some ups, we have downs. The down points are referred to as synclines, while the ones that bend upward are referred to as anticlines.
So what kind of fold is this? If you said anticline, it's correct. This looks like the letter A, and also the dip is outwards from the center. How about this? Anticline or syncline? If you said syncline, you're right. That is a syncline, and they are dipping inwards or towards the center. They are dipping towards the center of the feature. So that is the center. It's called the axis. We'll talk about the axis later. If you can recognize this area, this is San Pedro near Point Fermin, and here is the syncline. You can see the synclines. These are called gentle synclines, not bent very much like the folds that you have been seeing. You can see the rock layers are bent slightly, and they are dipping inwards, so that is a syncline. You got to go to the sea and look back to see this. Please don't lean over the edge to check this out, okay? It's very dangerous. Very rarely you will find a syncline by itself or anticline by itself. You always find a whole series of them: anticline, syncline, anticline, syncline, anticline, syncline, so forth. So they always occur in series. Here is a group of anticlines and synclines in Palmdale on Freeway 14. That's an anticline, and this part is a syncline. So now you can see actually anticlines and synclines share sides. These sides are called limbs. So anticlines and synclines share limbs. The imaginary plane that divides the fold, anticline or syncline, into two roughly equal parts is called the axial plane. So these green surfaces are actually axial planes. Axial plane. Any line on the axial plane is an axis. So this line here, right, like that, is an axis, and this line here is the axis. So axis actually defines the fold by defining the middle of the fold, approximate middle. Here is an anticline that shows what it looks like if you erode the top. So in this area, okay, this is an anticline, and here the anticline is eroded, broken and washed away. And you can see what it looks like in the inside of this anticline once it eroded. Now it's a good time to remind ourselves about the strike. So the rocks are going as shown by this arrow. So that's the strike direction, and of course you can see the dip. Interesting thing to notice about this dip is that the rocks are dipping outwards. Here is a drawing of monocline. Mono means one, cline refers to inclination, so only one side is inclined. In this case, this side of the structure is horizontal and this side is dipping or inclined. Again, we are looking at an anticline. And you can see the axial plane marked by this blue surface. So that is an imaginary surface that divides the fold, anticline or syncline, into roughly equal parts. It's never exactly the same, very rarely it happens, but generally equal parts. So you can see the rocks are dipping this way, and on this side they are dipping this way. So the two sides of the fold are called limbs. So in an anticline, the limbs are dipping outwards from the axial plane. Let's draw a fold, specifically an anticline. So we draw a curved line like this, and we draw just the right hand side of it here, and then join them with three lines, one there, one here, and half of the line right here. I hope you can see a folded piece of paper. Rocks just look like that. Layers of rocks also get bent or folded like this. So let's name this fold, all the various terms. Here, the two sides are called the limbs. And the point where the fold, the rock has bent, which is right there, is called the hinge. Hinge is the point of highest curvature. Here, look at the layer, it is almost straight. And here it's almost straight. But here it is highest bending is right there, and on this side is almost straight. So the hinge also is known as the point of highest curvature. If you join all the hinges, you'll get this line. We call that the hinge line. Now if you draw an imaginary surface right through the middle of this fold, so let's draw a dashed line like this, and that is an imaginary surface we call the axial plane. Any line on the axial plane is an axis. So that is an axis, that's an axis, as any line is an axis. But the hinge line is a very specific line, and that is the top of the fold in this case, or the place where, or the line where the rocks have bent. So these are the terms that we use to describe a fold. Let's define axial plane as the surface containing all the points of highest curvature for all layers. And an axis is a line drawn on the axial plane. Sometimes a fold can get folded. So the rock gets folded and the fold gets folded again and again and again. So that you can have very complex deformation patterns. Let's say we find a rock layer bent, folded like this, and another one like that, and another one like this. Now if you look at all the hinges or the points of highest curvature, we put one in the middle to show the approximate middle. We join all this, that is an axis. That's axis number 1. Now if you look, axis is bent, and all the rocks are bent here also. So what does that mean? That means that we have a another set of points of highest curvature that defines another axis like this. So we call that axis number 2. And then you notice this axis also is bent, which reminds us there's another axis like that. So folds can be bent over and over again, multiple deformations or multiple stresses in the same deformation. It's hard to decide which one is what, but we can tell which one happens first, which axis is last. Can you take a look and let us know what is the first formed axis? You are right. The straight axis is the last one, that therefore this is the youngest. And the axis of that and the limbs of that fold represented by that axis makes the next one, which is this one, and axis 1, which is the first folding, is the oldest. So you might find something like this in a test and you figure out which axis is the youngest, which axis is the oldest. Simply the youngest one is a straight axis and the oldest one you have to decide which one is which. It's not hard if you think about it. Think about all the hinge points and then join the hinge points and you can see the axis, which one is bending what. Here is an example for a folded fold. You see an anticline in here, and on the side you see another anticline. So one anticline is folded into another anticline. The resulting feature is called a dome. And a syncline seen here, if it is folded into another syncline, then you have something called a basin. So a dome is an anticline folded into another anticline, and the basin is a syncline folded into another syncline. Not all folds are horizontal. Most of them actually dip. So these dipping folds are called plunging folds. If you want to define a plunging fold, it is actually folds with dipping hinge lines. I would like you to go back to look at the diagram that we described the fold and their terms. The hinge line actually is kind of the line where the rocks have bent along. If the hinge line is horizontal and not dipping, it's called a horizontal fold. We can identify these dipping folds by noticing their V-shaped outcrop pattern on the surface. Let's take a look at it.
Be it a syncline or anticline, has a plunge into the earth. In other words, what will it look like at the surface if the fold ridge is not horizontal but tilted? Imagine taking a bunch of layers and making them into an anticline, and then dipping that fold into the ground and shaving it off level. Instead of symmetrical layers and stripes on either side of the axis of symmetry, we see a V-shape form at the surface. With a plunging anticline, we will see the oldest layers in the center still, and youngest layers on the flanks, and the layers all dip away from the center of symmetry just like with any other anticline. The V shape at the surface also tells us which direction the fold is plunging into the earth. With a plunging anticline, the V points in the direction the fold is plunging into the earth. With a plunging syncline, the V points in the opposite direction of plunge. But as with any other syncline, the youngest beds are in the center, and all flanking beds dip inward towards the center of symmetry. Besides level and plunging synclines and anticlines, we can further classify folds as being symmetrical or asymmetrical. Isoclinal when the limbs parallel each other, overturned when one limb ends up upside down, similarly overturned recumbent when the fold axis is near horizontal, and chevron when they zigzag. Regardless of specifics, almost all folding is the result of compressive stress and ductile strain.
Let's see the difference between a horizontal anticline and a plunging anticline. Here is a horizontal anticline. The dashed line is the horizontal, and if you draw two lines on the limbs, if you cut it up to that level and if you look from above, what you see is called the outcrop pattern, and what you're going to see are two parallel lines. So the lines are straight. So outcrop pattern is straight and parallel. But if you look at a plunging anticline, here is the plunging anticline and here is the horizontal, and this angle we normally call the dip if it is a rock, but this one is a fold, so it is called the plunge. The outcrop pattern of a plunging fold, if you erode up to this line here, right here, so if you erode or just cut everything down to this level, this is what you find on the surface. So the outcrop pattern is V-shaped. I'm sure that you can see this V shape right here. Okay, so when you see a V shape, you are looking at a plunging fold. Horizontal and plunging synclines are the upside down of the previous diagram. So we are looking at a horizontal syncline here. If you draw two lines on the limbs, you'll see on the surface the outcrop pattern will be two parallel lines. If it is plunging, you can see the dip is called the plunge right there, and the outcrop pattern will be a V-shaped. I would like you to compare the two diagrams and figure out how you can tell what plunging fold it is. Is it plunging syncline or plunging anticline? Both of them have a V shape, but there's something about the V shape that you can tell which one is what. I would like you to try it yourself. Here is the drawing of a series of anticlines and synclines. Remember, anticlines are always separated by synclines. Synclines are always separated by anticlines and so forth. So we have a plunging anticline here, plunging syncline here, and plunging anticline again. Look at the V shape. The V shape for this plunging anticline is like that, V shape for the outcrops, and the plunging direction is the same. So for plunging anticlines, V shape is the same direction as a plunge. For plunging synclines, the outcrop looks like this, and the plunge is in this direction. So plunging synclines, the V shape is one direction and the plunge is in the opposite direction. Okay, so the V point away from the plunging direction. That's how you identify a plunging syncline and plunging anticline. Here is the satellite image of Western Himalayan mountains again. You can see the V-shaped outcrops. These are actually mountains, thousands of feet tall. From there you can see that these are plunging folds, and all this also indicates plunging folds. So these are hundreds and hundreds of miles across. Again, every time you see a V-shaped outcrop, you know these are plunging folds. Again, this is the Indian plate colliding with the Eurasian plate, and all this here used to be an ocean, and all the mud and the sand that was at the bottom of the ocean now is squeezed in, making this giant Himalayan mountain range. And underneath this you will find metamorphic rocks. At the top you find sedimentary rocks that are not metamorphosed yet. Another way that folds can be found is actually the way they are seen from the side. So normally if you find a fold like this, you are looking at the side view, so this is called an upright fold, and the fold look like this is overturned, and then a fold like this is called recumbent. What's the difference? If the axis is making between 90 degrees to the horizontal, that means vertical, and 60 degrees, it's an upright fold. If the axis in between 60 degrees and 30 degrees from horizontal, which is like this, that's 0 degrees horizontal, then it is called a recumbent fold. So if a fold axis falls here, that would be an upright fold. If the fold axis falls in between these two lines, it's an overturned fold, and the last one will be recumbent fold. So those are overturned folds and these are recumbent folds. Here is the set of folds. I'm sure you can see the rocks being folded. So this rock layer is folded like that, and this rock layer is folded like this. We can now draw the axis. If you draw the horizontal, it would look like this. And the angle here looks like a little bit greater than 30. So this is the overturned fold. This is an overturned fold. Here is a fold from San Pedro, Royal Palms, County Beach. You can go and see it. You can see that the rock layers are bent or folded like this. And they are bent like that. So if you draw the axis, it will look like this. Now this axis is making about maybe 20 degrees, 15 degrees to the horizontal, which is right there. So it's very small angle. So these are actually recumbent folds. Each one layer is recumbent fold, but together we call the whole thing a recumbent fold. This is the side of the Freeway 14 in Palmdale. They cut this to make the freeway, and now you can see the folds in here. And these are the fold axes. And they are somewhat between 60 degrees and 40 degrees, so these are overturned folds. Here is the same place, looked from far or photographed from far. You can see the different folds have different axes. So from the orientation of the fold axis, you can tell what kind of stresses were acting on this area. Again, just to remind you, this is the location where the San Andreas Fault crosses the freeway. Let us talk about the second group of geologic structures, faults. When rocks break, they break along a surface and the rocks move along this surface. So faults are the surfaces along which some movement has taken place. So we can write faults are surfaces along which rocks have moved. They are caused by all types of stresses: tension, compression, shear, and hydrostatic. When rocks break, not only they move, they also emit energy that was stored in the rock. And that energy goes everywhere, and we notice them as earthquakes. So we write faults are associated with earthquakes. There are two families of faults. The first one is called dip-slip faults, and the other one is called strike-slip faults. Let's first talk about dip-slip faults. Dip-slip faults is when the rocks move vertically, up or down. So we say dip-slip faults have a vertical displacement. They are caused by tension or compression. There are two families, two types. The first one is called normal fault, which is caused by tension. The other one is called reverse fault, which is caused by compression. When the reverse fault angle is close to 0, they are called thrust faults. Let us talk about the first family, the dip-slip faults. Here's a photograph of a normal fault. You can see the fault right here along this line right here. And you can see that this rock is displaced and now it is here. So either this side went down or this side went up. So when you see these arrows are half-headed arrows, and that's how you indicate movement along a fault. So this is a normal fault. Sometimes you can have multiple faults. You can see 3 faults here, 2 major ones here. From there you can see that this side has gone down compared to this side gone up, and this side has gone down and this side has gone up. So these are normal faults. Here is a normal fault seen in nature. Here is the most visible rock layer in here, and that rock layer stops right here and then shows up again here. Clearly it was broken and shifted. Now if you look, you can clearly see the fault. It is not a perfect straight line. You can see the size of the fault compared to the person standing nearby. You can see that either this side went down, so you mark like that, or this side went up. We cannot tell which happened, but we know relative to each other they moved like that. So this side moved down or this side moved up. This is the fault, and this side is called the hanging wall, and this side is called the footwall. Let's draw this diagram. So here's what normal faults look like in theory. That's the fault, because the 2 rock layers are actually used to be one that broke and moved apart, making that side slide down or this side moved up. So this is up and down movement. We are looking at a cross section. We are looking sideways at a bunch of rocks like we saw in the last photograph. Here is the movement, and that's where the rock used to be, moved so much down, so that's called the displacement, and this is the fault. Although we see that as a line, it really is a surface that extends into the ground, into the cross section, into the profile, into the cliff. So the fault is represented as a line on the side view. So this is what a normal fault looks like. To define a normal fault, we need to understand 2 terms, hanging wall and footwall. These terms actually came apparently during the early mining days in tunnels. Hanging wall, apparently that's where they hung the lantern and they were standing on the footwall. So in normal faults, hanging wall has gone down. You can see it right here. The hanging wall side has gone down and the footwall side has moved up. All you have to do is to remember one. So we'll remember always the hanging wall, what the hanging wall did. In the normal faults, hanging wall side or hanging wall moves down. Like rocks, faults also dip. Let's see what it is like. Here is the horizontal surface and here is a fault, and this fault is dipping like that, and this fault is known as a fault that is dipping to the left in this diagram. And if the fault looks like this, the dip is like that, and this is a fault that is dipping to the right. Some faults are vertical, so they are called vertical faults. And there are no horizontal dip slip faults. Talking a little bit about hanging wall and footwall, let's see, that's a fault. So the side above the fault, there are two sides. This is above the fault and this is below the fault. The side above the fault is called the hanging wall side and below is called the footwall. Now if the fault looked like this, is dipping to the right. This fault, the first one is dipping to the left and this one is dipping to the right. So this fault is dipping to the right and that is the hanging wall side because that's the side above the fault, and this is the footwall side. That's because that side is the side below the fault. So always remember what hanging wall and footwalls are. This is true only for dip slip faults. In contrast to the normal faults, reverse faults are caused by compression. You saw in the little video before. So the hanging wall side moves up. Let's draw the terms for reverse faults. Here is the rock that is being displaced along this fault like that. So that's the movement, and the displacement is like that. That is the fault. Here the hanging wall side has gone up and the footwall side gone down. Just remember one, the hanging wall side or the hanging wall itself has gone up. Again, all these illustrations and little notes are on a page that says notes for structural geology. It's in the module. Make sure to print it out and refer to this when you take your notes, when you study. What we are saying here is actually shown in very short notational form. Okay, so print that out and keep it with your notes. Again, this is what the reverse fault looks like. Here is an example for a reverse fault.
Faults. A fault develops where a rock structure is broken and forcibly displaced. The movement along a fault may be vertical, horizontal, or a combination of both. A normal fault develops from tensional stress, the stress that results when a landscape is rifting or pulling apart. Movement along a normal fault is predominantly vertical, although the orientation of the fault plane may not be perpendicular to the surface. As the landscape is extended, notice that one side of the fault plane drops down relative to the other. The fault scarp formed along the uplifted mountain front eventually erodes away, leaving little surface evidence of the fault. Many landforms can develop from normal faulting, including tilted fault block mountains, down-dropped basins known as grabens, and uplifted mountain blocks called horsts. A reverse fault develops from compressional stress. Movement along a reverse fault is also predominantly vertical, although in a type of reverse fault known as an overthrust fault, the upthrown block overrides the downthrown block at a very low angle.
When the rocks near the surface undergo faulting, they form different types of landforms. Here we have a normal fault where the hanging wall side is going down and the footwall side is going up. And that pretty soon will undergo erosion, especially the part that is above. This part is high, so the streams will start going down and it will create a landscape that looks like this. And in the case of a reverse fault, the hanging wall side has gone up, the footwall gone down, and it will create an elevated area like this. So there will be, when it rains, the streams will come down and erode, which will result in a land form that looks like this. And if you look at that, both landforms from above, they look the same. They both have hills and they both have a flat area, and then you have mountains. So when you look at a regular landforms, when you drive around, you don't see what happened where, when. They all look natural, but now you know underground a lot of things have happened, could have happened, and that causes formation of new landforms. And erosion is a serious factor. Erosion, this is what you are seeing here, mid erosion. So this is the starting, and this is the second stage, and the third stage would be flat. So let's look at an example of this. When you drive around California, especially in the desert area, you might see some regions like this. You'll see that your freeway or highway is in the flat area, and above that, on the background, you'll see mountains. We can't tell what happened, but in general sense, we can say that's where the fault is. And we think that side has, the mountain side moved up and the flat area has moved down. This is what we normally think most of the time. In California, it is true, but sometimes it could be different. So we have to dig down or go through the river valleys. For example, you have to walk along this area to see what the rocks have been doing. Look on this side, look on this side, then you can see what really has happened and compare with the rocks on this side. So that is called geological mapping, and that's how many geologists figure out what exactly happened in this area. Sometimes you find faults in a very interesting situation. For example, right here is a fault, and it is dipping to the left. And here's another fault, and it's dipping to the right. It is clearly visible that this side has gone down relative to this side, which has gone up. This side has gone down, which is the hanging wall, and those are normal faults. The interesting thing is to notice that the block in the middle has gone down. It has fallen down. This is an interesting structure called graben. And the other sides, we cannot see the top. They are called hosts. So that's host, and that's the host. Here's a graben and host structure in an illustration. We see these are all normal faults. The hanging wall side has gone down due to being extended in this direction. So that it was pulled apart, or tension was acting on this region, causing the two sides to be pulled apart. So the grabens sink, leaving the host around. So you have valleys formed, separated by ridges. So that's the graben and host structure, indicating that this area has been extended or subject to tensional stresses. Let's talk about the second type of fault family. These are called strike-slip faults. Strike-slip faults are formed when the rocks moved horizontally. Unlike in the dip-slip fault where the rocks are moving vertically, here the rocks are moving horizontally. So we say strike-slip faults have horizontal displacement. There are two types of strike-slip fault: left strike-slip faults and right strike-slip faults. Here is a drawing of a left strike slip fault. So you see two rocks are displaced along this line, and if you stand on one side and look at the other side, and the other side has moved to your left, and if you stand on this side, this is, and look towards the opposite side, and then you can see that from this side the motion on other side of the fault is also left. So no matter which side of the fault you stand, the other side has moved to left. So this is the fault, and that's the movement, and this is a left strike slip fault with a displacement like that. Let's draw a right strike slip fault. Here are the two displaced rocks displaced by along this line, which is the fault. And if you stand on this side now and look to the other side has moved to the right. Doesn't matter what side of the fault you stand, the other side has always moved to the right. So we can continue the diagram. That's the fault, and that's the other side is moving to the right, and that's the symbol for this side. So this is a right strike slip fault. Here is a satellite image of the Earth's surface showing a strike slip fault. Can you guess? Is it left or right? Let's see. You stand on this point and look to the other side. Or you can stand here and look to this side. You'll see this light colored rock which is here and is on this side is here. So the light colored rock has moved to your right. When you stand from here, stand and look from here, the other side has gone to the right. So this is a right strike slip fault. You can use the hyphen or you can skip the hyphen. So it's a right strike slip fault. Here's another satellite image showing another fault. You can see this is the strike slip fault. And you can see that these gray colored rocks right here are now found here. If you stand here and look to the other side, you'll notice the movement is not to that side, and that's left. So this is a left strike slip fault. Here is an illustration that shows how strike slip fault look like when you see from above, and also if you can see underground. Here is the strike slip fault, and you can see a stream coming from here, and it gets in the fault and then it moves around the fault, and now it is found here. Stream is flowing that way. So if you stand here and look the other side, the stream has moved to the right. So this is a right strike slip fault. There are some features that you might find in some kind of faults like this. You might find a valley that is very straight. So it's called a linear valley. And sometimes you can find lakes, small pools of water collecting there for no reason. So there are no dams. So just these are natural lakes, natural ponds. These are called sag ponds. So this is what you see when you look at the world's most famous strike-slip fault, San Andreas Fault in California. Here is the San Andreas Fault seen from air, somewhere in central California. You can see the movement is like this. How can you tell? Well, you can see the streams are coming down like this, and the stream is going along the fault, and now it's going this way. So if you stand here and look to the other side, you'll see the stream side has moved that way. So that's the right. So this is the San Andreas Fault. It's the right strike slip. This is the North American plate. This is the Pacific plate. And that's the plate boundary. San Andreas Fault starts in Baja California, Mexico, and then comes into Palm Spring, Indio, then continues passing Los Angeles right here. It's a little bit to the east of us on the way to San Bernardino on 91, you can see that. Then it continues towards Northern California and gets out to sea around San Francisco, eventually in Arcata, California area. So that's the San Andreas Fault. It is associated with other faults, for example, Garlock Fault, Owens Valley Fault, and all kinds of other faults. So California has a lot of faults. Most of them are strike-slip faults, especially when you look from above, you can see all these strike-slip faults. These ears indicate the earthquakes that has taken place along these faults. When they were taking photographs and flying over California, they found this very long lake that is almost a whole set of lakes that almost forming a straight line. And this is an example for sag ponds. So this is actually theoretically a sag pond, because they found out that this is the path taken by a very big fault system. So there's a fault running through that, and this fault runs from Southern California all the way to Northern California, and they name this fault after the name of this lake. So this fault is called San Andreas Fault because the name of this lake is San Andreas. Sometimes faults are hard to see. When you see a dramatic change in rock types like the one that you're seeing here, you can suspect that this is a fault. We are not sure, but this side, the rocks are very different from this side. So that's most likely a fault. We cannot make conclusions until we go and check the rocks and make some data, and that's called geological mapping, and that's what sometimes faults look like. When you walk around, you might find surfaces that are fresh, no vegetation. Then you realize maybe this side has fallen down and this side has gone up. Since the fault is dipping towards you in this photograph, this looks like a normal fault. So we can actually conclude that this side has gone up relative to this side, it has gone down. Again, faults are not very obvious in some situations. Once you get used to that, you can tell a fault when you see one. In Southern California, there are lots of faults. If you look at this is Los Angeles. This Palace Verdes Peninsula right here, downtown LA right here, Harbor College right here, and this is the San Andreas Fault, marking the plate boundary between the North American plate and the Pacific plate. And if you look carefully, you can see lots of other faults. So this is Santa Monica Mountains, and that's the Santa Monica Fault. And these are San Gabriel Mountains. So these are the San Gabriel Fault. It's a very complex set of faults because this is a plate boundary zone. You have you have so many faults. Geologists have thought maybe we have seen all the faults, but then in 1994 there was an earthquake in Northridge right here. Sorry, Northridge is not here, Northridge is right here, and that's a fault that they did not know exists, so they call them blind faults. Here's another closer look at Los Angeles area. This is the Santa Monica Fault, and this is the Palos Verdes Fault, which goes right through the harbor, through Los Angeles Harbor College, and eventually gets out at Redondo Beach. So there are quite a few frequent earthquakes along these faults, and the next time you feel an earthquake in this area, you'll tell yourself must have been along a fault that is very close to us. We have a whole set of faults. Newport Inglewood Fault is a very active fault. We are really concerned about all those faults. And again, in this distance is San Andreas Fault. And if you take another closer look, you'll find all the different faults. Here are the names that you found in the previous image. So all these little abbreviations represents all the faults. Another type of structures that we talk about in geology are called joints. Joints are parallel fractures in rocks. They are caused by all kinds of stresses. They normally belong to a system. For example, here's a set of fractures that you find in rocks. This is considered a one system of joints. Here is the photograph that shows well-developed joints. You can see these lines here and here and here. All these are fractures parallel to each other. So that is one system. They all belong to a single system. Then you have these fractures like that, these, and those. These are another set of joints belong to one system. The surfaces themselves are a joint surface, so they belong to another system. So this is a classic example of how joints look like. So next time you see rocks fractures like this, you can tell yourselves, and these are joints, and then you can count the number of systems in this area. Sometimes joints are kind of hard to see, but this is a joint, and that's a joint, and that's a joint. So these are all joints. So you can see all these joints are parallel to each other. When you look at rocks in deserts, for example in Joshua Tree National Park desert, you see, when you see rocks like this, they are caused by joints. So here is a joint, joint. You can see all of them belong to one system, and then there's another system like that. So if you look carefully, you'll see generally three sets of joints. And yet another example of joints. Along this joint, water has collected and it has caused chemical weathering. So you can see there's quite a bit of chemical weathering going on along this joint, and then that's the one system, and here is another joint system. They are somewhat parallel to each other. That is a second system. And all along these joints, water has percolated, penetrated, and caused chemical weathering. You can see that it separates these blocks of rocks that will eventually get smooth and round because of the spheroidal weathering. Please check your weathering lecture video. You'll see a little reference to this photograph. This is a great example for how spheroidal weathering starts by water collecting along joints. Here is a joint system, and here's another joint system, and here's another one. Sometimes you find all kinds of joints crossing each other, and somebody asks you how many joint systems are here. You say 3. That brings us to the end of this discussion on rock deformation. We talked about the 3 major geologic structures: folds, faults, and joints. There are some other minor structures called lineation we didn't talk about. That's okay for now. So if you have any questions, let me know. You can email me. Otherwise, have a great day.